Hydrogen's density is much lower than that of air. Hydrogen inside a chimney or pipeline would be considerably less dense than the flue gases, and thus the column of air outside the chimney or pipeline would have a greater driving force to push the hydrogen up the chimney or pipeline from a lower to higher elevation. This effect would be even more dramatic if the hydrogen were produced by electrolysis deep below the surface of the ocean. Atmospheric pressure at sea level is around 100 kilopascals, but only 9.8 meters below the surface of the ocean, the pressure increases to 200 kilopascals, or 2 atmospheres. If electrolysis took place 500 meters below the surface, the hydrogen gas would be reduced under pressure of roughly 50 atmospheres and would arrive at the surface at approximately the same pressure. Producing pressurized hydrogen would lower the effort required to compress the gas for transportation in a tanker and would facilitate the transport of hydrogen through a pipeline from the source of production deep in the ocean to land. The buoyancy of hydrogen affords great potential to move the gas to locations where it can be used without the need of additional mechanical or energy inputs. Hydrogen and oxygen combine in a hydrogen fuel cell to produce electrical energy in a process essentially the reverse of electrolysis. A fuel cell uses a chemical reaction to provide an external voltage, as does a battery, but differs from a battery in that the fuel is continually supplied in the form of hydrogen and oxygen gas. It can produce electrical energy at a higher efficiency than burning it to produce heat to drive a generator because it is not subject to the thermal bottleneck from the second law of thermodynamics. The only byproduct of a fuel cell is water, so it is pollution-free. All these features have led to periodic great excitement about fuel cells' potential, but we are still in the process of developing that potential as a pollution-free, efficient energy source. One of the main advantages of a hydrogen economy is that the fuel can replace the fossil fuel burned in internal combustion engines and turbines as a primary way to convert chemical energy into kinetic or electrical energy, thereby eliminating greenhouse gas emissions and the pollution from internal combustion engines. Hydrogen has a high energy density by weight and is highly flammable, needing only a small amount of energy to ignite and burn. High capital costs of fuel cells is one of the major obstacles to their development. In 2002, typical fuel cell systems cost $1,000 US per kilowatt. But by 2009, the Department of Energy reported that 80 kilowatt automotive fuel cell systems in volume production of 500,000 units per year had come down to $61 per kilowatt, while their goal for considering fuel cells to be competitive was $35 per kilowatt. The cost of production and use of hydrogen must also be seen in juxtaposition to the $28 trillion in coastal infrastructure the world is potentially confronted by. A November 2010 Environics poll indicated that over 70% of Canadians concur with Ms. Figuere's conclusion that military spending should be redirected towards efforts to reduce greenhouse gas emissions. And it has been noted that OTEC research is being sponsored by the Department of Defense in the U.S. and DCNS, a French naval vessel and marine energy technology company. In this regard, Lockheed Martin is the principal benefactor of the Department of Defense funding, and their research is focused on the problem of large cold water pipes, a technological dead end that makes OTEC both overly expensive, environmentally damaging, and ensures that it can never meet the entire global need for primary energy. The solution will be provided in the next installment.